Well, thank you for allowing me the chance to present an engineer's perspective on global warming as one of practical concern about what we should be planning for and designing to if we're not to be negligent. Surely the role of the engineer has always been to take up scientific knowledge and engineer it into something useful. This has been my approach to the science of climate change. And so, looking at the globe here, another chance to behold our beautiful planet Earth as she appears from nearby space. An orb of stardust warmed by sunlight, supporting a thin, fragile shell of air, sea, and land, a shell that is our world. A world so precious as to be the origin and home of abounding life. Life forms, each and every one, utterly unique in the universe. Life forms, each and every one, the distinctive embodiment of untold knowledge. A shell that is our world, a living world, a knowledge base so vast and profound as still to be, at least by us, almost entirely uncharted. There have been 4 great paradigm shifts in the Earth sciences, all true revelations that drastically changed our basic ideas. The theory of evolution, 1860s, the theory of ice ages, 1900s, the theory of plate tectonics, 1960s, and now the theory of global warming, 2000s. I'm about to present you an overview of the global warming processes. This is a presentation of 10 slides. And it should take me between half and 3/4 of an hour. So don't worry if you find some of the material confusing. We can always Skype later and sort that out later. Yep. Now, there's a dismaying amount of misinformation on global warming streaming around society these days still. So for this presentation, I'm going to disclose my methods and the sources of all the data up front, now rather than later in an appendix. So the science used to look into the natural phenomenon of greenhouse warming and in developing my engineer's model of the process is fairly standard university physics science, with the detailed explanations of the methods and techniques presented in IPCC science articles and reports, available on the IPCC website. Young and Friedman's University of Physics. I've got the current edition 14. I started off with edition 8. Apparently there's an edition 15 now. This is one of the most widely used introductory textbooks in the world. Yale University's open course here, The Atmosphere, the Ocean and Environmental Change, well taught by Professor Ron Smith, free on the internet. You get 36 hours of him on YouTube. And I did the whole lot. If you paid $100, you could actually sit the exam and be certificated for it. It's one of the gifts the US does to the world by providing all this information free. And of course, featured articles in the General Knowledge Center, Wikipedia. The data used is sourced from respectively, I better say here, there is the latest Physical Science Basis report in 2021 from IPCC. God, they are dry things to read, hundreds of pages, and you come away, I don't think, knowing very much more than you did when you started. But anyway, there are pointers to it, and a lot of the papers they point to are even drier. But the other data used, respectively, for carbon dioxide and water spectroscopy data, I'm using the Harvard-Smithsonian Center HYTRAN online, a database of high-resolution transmission modular absorption parameters. And for climate data in general, the US government's administration, National Oceanic and Atmospheric, NOAA, and National Aeronautics and Space, NASA. NOAA and NASA, together with a staff of thousands of scientists, engineers, and technicians, administer to hundreds of ocean buoys, thousands actually, thousands of ground-based weather stations, a daily release of around 2,000 weather balloons, and dozens of satellites providing live and global information on atmospheric CO2 levels, moisture content, and of course surface temperature. We're only a few slides away from seeing how these satellite images are made. So looking at the world, our beautiful world, a shell that is our world, so precious as to be the origin and home of abounding life. How privileged we are. But now to model the climate, where to begin? Climate is what we expect, the weather is what you get. According to Mark Twain, no help. Well, keep it simple, stupid. Everything should be as simple as possible, but no simpler. Who said that? Einstein. Climate is the average weather. Weather is the local atmospheric dynamic. So we'll model the climate as a cross-section of a one square meter column filled with the global average of everything, both atmospheric and in the oceans. That's composition, surface temperature, pressure, irradiance, albedo, and so on. So we start by looking at what the atmosphere is. Spain from space. The Earth's atmosphere, as it turns out, is a well-mixed composition of gases, nitrogen, oxygen, argon, moisture, and CO2 and other traces. Collisions between air molecules keeps them aloft with heat conduction at the surface, boosting their kinetic energy, and gravity having most of that energy returned. What goes up must come down. Once set going, the balance system is practically perpetual, so conductance won't therefore figure in our model. Even with wind, what goes into the atmosphere will fall out of it eventually. It's a balance between gravity and surface heat putting it up and gravity pulling it back. And we won't be worrying about conduction. On expanding our view, we see that the atmosphere is layered, with gravity holding the atmosphere close. The pressure and temperature gradients naturally have the air thicker and warmer at the surface and thinner and cooler at altitude. The pressure gradient is clearly exponential, and so would be the temperature gradient if not for the Earth's ozone layer at altitudes of around 25 kilometers. The common gas law is good for modeling and adaptations of it up to about the troposphere, but look what happens when the ozone effect comes in. And this is unique. This is one of the wonderful things about our planet. The temperature, ozone is breaking down as an exothermic reaction. So we would expect the air to get cooler as you go up and lower pressure as part of the gas law. But when you get up to a site above the troposphere, a height above the troposphere, the ozone heat means that the air above it is warm. And this traps all of our weather into the troposphere, because for convection, warm air rising has to have cooler air to rise into, or cooler air has to have warm air to fall down through. But when you've got warm air coming up and the air cooling off, but when the air above it is warmer, it can't get any higher. So this is really where that traps most of the moisture content and our weather at an altitude of around 11 kilometers. So we've got this, all our rain and all our weather happening in that time. So nothing really escapes from convection heat. That is from evaporation and condensation. What you put in, you eventually get back, wind, and so on. So warm air, being more agitated than cold, pushes out to take up more space, and so is thinner and buoyant and cold air. Cold air tends to sink down through warm air. This activity sets up convective circulations capped by the tropopause. Within a circulation, as a packet of warm air rises into altitudes of less pressure, the packet expands doing work and loses heat. When the same packet now of cold air sinks back into higher pressure, it contracts, work is done on it, and it gains heat. In completing a cycle, the internal energy of the packet doesn't change. The convection process is practically adiabatic, and convention won't therefore figure in our model. Now, returning to our column, an atmospheric pressure of 1001 kilopascals at the surface means that we have about 10.3 tons of air in our climate column and 6.3 kilograms of carbon dioxide. Some 86 times 10 to the 24 molecules, enough for 8 million layers. If you laid out all the carbon dioxide over your square meter, you would have 8 to 10 million layers of it. There's a very real and significant probability that a photon traveling up the column will encounter a CO2 molecule. Such probability, though, is pressure and temperature dependent. We'll have to step up through the atmosphere, but in practical engineering fashion, we don't need to be too fussy. I'm going to step through it in a third. A third of the molecules. There's a third of the molecules just over 3 just over 3 kilometers high. So at a mean height of 1.65 kilometers, there's a third. That's going to be our average for a third. The next third of the molecules happens at a height of 5.85 kilometers, going up to 9 kilometers, and the final third is of a mean height of 13.4. No, 14.2 kilometers. So when we do our analysis, we'll be using pressure and temperature at each of those three when we step through, when we model the weather. So there will be feedback when we'll actually add extra moisture and so on into the air. So we'll actually have to rework out what the temperatures and pressures are using partial pressures and so on for moisture content. So here's the question. This starts the energy balance model. What heats the surface and how? Well, yes, it's sunshine. The wonderful, satisfying experience of sitting warmed by the morning sun and your first cup of coffee, or when in the outback. The sun radiates energy in the form of photons that stream through the electromagnetic field of space. In envisaging this, I'm happiest with the idea of electrons being wave packets. The shorter the wavelength, the tighter the packet. It takes photons streaming out of the sun 8 minutes to arrive at the surface of Earth, where a process of absorption, their energy is transferred into vibrational warmth. The sun radiates, the Earth is irradiated. Now, when we measure the intensity of the irradiance, we find that it's related to the wavelength of the arriving photons, with the relationship taking on a curve of this form. For our sun, the maximum intensity is at the green-yellow wavelength, central to the visible spectrum. Warmer bodies, all warm bodies radiate, cooler bodies radiate in flatter curves with maximums at longer wavelengths, hotter bodies in sharp curves peaking at shorter wavelengths. So if our sun was a blue star, our eyesight would peak, our eyesight peaks at yellow-green. So it means that we did evolve on this planet, at least in the last 500,000 years. The sun has been fairly constant. If it was a blue star, we would be peaking in the blue area, and if it was a red giant, we would be presumably evolved to be peaking in the red area. Now, this relationship is modeled by Planck's radiance intensity equation as a function of radiance wavelength and the radiating body's surface temperature. This is a universal law of nature. Now, using Planck's equation and looking at the peak of the yellow-green, we can work out what the temperature of the sun is. And with that, we can work out the radiance per square meter from the sun, and looking at the angle to extend from the center of the sun to a 1 meter on its surface, looking through to what we receive at Earth. We can work out the irradiance, calculate the radiance that we're receiving, and then measure it anyway. And then the Earth, I wanted to use averages. So what the sun sees, or what's received from the sun, is like a disk going around the sun in orbit. So we take the disk, pi r squared, the area of the disk, and then we wrap it around the whole sphere, because the sphere is spinning. So it's fine to wrap it around the whole sphere with the area of 0.4 pi r squared. So what we're getting from the sun in watts per square meters on average over the planet is a quarter of that. 340 watts per square meter are arriving at this kangaroo. And he will get warmer under that radiation until he's emitting the same amount that he's receiving, and that's the energy balance. If he emits more than he receives, he'll feel cold. Well, the other way around, right? We'll follow that. So there's the Earth receiving in Australia the full 340 watts per square meter. And we'll just have a look at the energy balance on Earth. Then we're squashing up what we get from the sun in the yellow curve. The irradiance from the sun, and the Earth itself will be in balance when it radiates its own heat. Otherwise, it will carry on getting hotter and hotter. So because it's fairly stable, then it has to be radiating what it's receiving. When we look at the Planck's law, we can integrate that, and we find the heat and the energy in watts per square meter with an integral under the curve, the area under the curve, and that comes to a constant with the temperature to the power of 4. So that's how we find, if we know the temperature of the surface of a black body, we can then work out how many watts per square meter are being irradiated from it. And if we look at the formula and take a derivative test to find the peak, the maximum wavelength, if we know the maximum wavelength, then we do the derivation, we can get another. This is how we can find out T. It's another constant with the temperature underneath. So once you've got T, you can then go and work out the watts per square meter of any black body. That's what Planck's law has given us. Now, the other thing that's going to play in here is clouds reflect some of the incident sunlight away, and so do the pole, as do bright surfaces, particularly ice, with these effects collectively termed albedo. There are different values of albedo, one for clouds and one for the ice caps, and we'll account for these in our models. The combined value for the Earth is currently around about 31%. So with the energy balance, we can look at what's happening to the Earth. So we're getting 340 watts per square meter up at the top of the clouds, albedo is reflecting back 105 watts per square meter, meaning at the surface, we're getting 235 watts. Now that means for balance, we have to also be emitting 235 watts per square meter. And when you put that T in to your equation, you find that we have got, when we put that in and work backwards to find T, we find that that would be an Earth with a mean temperature of minus 19 degrees Celsius. This would happen if there was no greenhouse gases.
Thank you, Tom.
So we can be very grateful that there were greenhouse gases.
And to go and get Richard at 9, yeah? Or before 9.
Minus 19. So we know that we're not minus 19. Instead, we know that we're lovely at the moment. The average temperature is 15 degrees Celsius. So if you put 15 degrees into this formula, you'll get a curve which says that we are emitting 390 watts per square meter. So the question is, what's making this difference of 155 watts per square meter? We've got 235 coming in, 390 going out. We've got to find 155 from somewhere. And while I'm at that point, this is a good time to get rid of the myths. The solar cycle is about 1 watt per square meter, but by the time at 1.2 watts per square meter from a peak to a trough, by the time it gets to our average surface, it's only 0.3 of a watt per square meter. So 0.3 of a watt when we need 155 is neither here, is just nothing. The solar cycle, flare cycle, as far as heat goes, is insignificant. So it's a red herring for people to say that it is. Now, the other great thing too, when you actually have a look at all the data on all the volcanic data on the planet, our thermal leakage is less than 0.1 watt per square meter. So our rocky crust turns out to be a really effective duvet cover. So even after 4 billion years, we've still got a very hot core. It's a very effective insulator. So the heat in global warming is not coming from volcanoes. Right. So what is it coming from? And that's where we've got to bring in a greenhouse gas layer. So as you're coming up, some energy, if energy is absorbed in the greenhouse gas layer, it will then be emitted. Half of it will go up, half of it will come down, basically from the layer. I mean, you know, it'll be emitted in a sphere, but cut the sphere in half, half's going upwards and half is coming downwards. So there's 155 watts going out and 155 watts coming in. The sum of those is 310 watts. Has to be being absorbed by the greenhouse gas layer. We're 390, so 80 is actually escaping right through. It's passing through the layer. 310 is absorbed in. Now we've got a full balance. And this is the energy balance of the planet. 235 watts plus 155 is 390. And then up at the cloud level, 340 coming in, but 105 plus 155 plus 80 is 340. We've got a balance. That's an equilibrium, state of equilibrium, where the planet will stay. Now, if you increase the greenhouse gas layer, this is what we're modeling. Now, which gases are greenhouse gases and why? We've got our equations again and the composition of the atmosphere. There's Planck's equation again and the Planck plots. It's irradiance and radiance in balance. So the area under what we get in is the same as the area in infrared degraded because of entropy of what we're giving out. The animation shows electromagnetic energy traveling across space. The absorption or emission of such energy requires physical shifting in space, either of an electric or a magnetic charge, plus or minus, or a north and south. For our purposes, we only need to be concerned with the electromotive force, the EMF part. This animation shows an EMF radio wave shifting electrons to and fro in an aerial as the signal is received and absorbed. Conversely, when an electric power supply and circuit shifts electrons, an EMF wave is transmitted. We might have learned in high school that at the subatomic scale, a photon is an EMF wave packet of nanometer wavelength, can cause electrons to jump between shells, shifting in space. The process is discrete, with each element having a distinctive signature of absorption and emission lines. Of the gases that comprise the atmosphere, nitrogen, oxygen, argon, carbon dioxide, and water, and traces, the spectral signature of each is the combination of the spectral lines of their constituent elements. These are the signatures of nitrogen and oxygen. But the absorption emission lines are prevalently at wavelengths of visible light and not at the infrared wavelengths at which the Earth is radiating. And so electron shell jumping doesn't figure in the greenhouse gas warming process. Now let's disappear the irradiance plot and enlarge the infrared radiance one for clarity. To see absorptions and emissions of infrared photons at wavelengths and micrometers, we need to climb up from the subatomic scale to the molecular scale. Here, to facilitate the physical movement of electrical charge in space, only those molecules that have the form of a dipole, that is, with a positive and a negative part, are contenders. This rules out nitrogen 2 and oxygen 2, but counts in both CO2 and H2O. Indeed, carbon dioxide and water vapor are the predominant atmospheric greenhouse gases. In a CO2 molecule, shared electrons tend to spend more time closer to the larger oxygens, making them slightly negative, and the carbon slightly positive. The molecule has several degrees of vibrational and rotational freedom, with more than 20,000 absorption lines. In an H2O molecule, shared electrons tend to spend more time closer to the larger oxygen, making it slightly negative, and the hydrogens positive. The molecule has even more degrees of vibrational and rotational freedom than CEO and has around 60,000 absorption lines. Molecular absorption spectra are measured using spectroscopes. This is a model made by the precision instrument manufacturer Bruker of Germany. Conveniently, the Atomic and Molecular Physical Division of the Harvard Smithsonian Center for Astrophysics maintains a public database, HITRAN Online, of spectroscopic parameters on an extensive range of molecules, from which I have downloaded full line-by-line sets for both CO2 and H2O. On closer inspection, the lines are actually distribution curves centered on specific wavelengths for which the HITRAN data set includes the intensity, wavelength, half-width, and temperature and pressure coefficients, enough information to work out the line's contribution to the absorption cross-section of our column in watts per square meter, up through the 3 levels. Now, another parameter they give in HITRAN is the absorption, the cross-section absorption coefficient. So that takes account of, we can work out from looking at the waveform how many watts per square meter a single molecule absorbs at a given wavelength. and then we can multiply it by the cross-section probability factor, and that takes account of the probability given the density of molecules in the column and the length of the column, the probability that a photon will actually encounter a molecule. And working against that is all of these molecules are capable of absorbing several photons at the same time. So it's not possible yet to calculate that, but these parameters are actually measured by these machines and provided. Now, to properly match radiated and absorption energies, it is necessary to step through the Planck curve in bands of wavelength, where for each band we work out what is being radiated, and then we look down at the spectra to see what is being absorbed. And so we've got to step through each of these lines to work out what can be absorbed at each of the frequencies, stepping through the frequency, stepping through each line, and doing it 3 times for each third of the atmosphere at a different pressure and temperature. Quite a lot. You need a big program to do it and time for the computer to do that. If we are absorbing radiation from space and observing radiation from space in the satellite, this is a typical spectrum on a typical day of what's happening. And there you can see what's being absorbed. All this is mainly water. Here is a big carbon dioxide. This is carbon dioxide. This is water. So we can see the effect straight away. You add more carbon dioxide in, there's going to be greater absorption. Now, which what my model is doing. Now, as alluded to earlier, looking through the spectrum, so if we look through an area where it's just carbon dioxide absorption, satellites can then make a map of the carbon dioxide content of the atmosphere looking down it. So it's looking through, it's measuring what's been absorbed. It knows the shape of the curve from the surface temperature measurement, in the satellite, and from then on it can actually start to do a plot information on the carbon dioxide levels in the atmosphere. So we don't need balloons or test stations to measure it all. Satellites can pick it all up now. I think that's a fantastic advance that we've done in my lifetime. And if we have a look where the water is absorbing, we can then measure the moisture content in the atmosphere the same way. And of course, if we come down through this gap here, this wonderful gap where nothing absorbs, that's your infrared spectrum. And if there wasn't a gap there, we wouldn't have infrared technology, because everything would be blurry and useless. But there is this area in here where nothing absorbs, and that allows us, all of our industry, infrared industry, to work, infrared cameras and so on, to work. And through that, you can look at the surface here, and you can measure the temperature and then come back into to what curve you're doing, and then you can do a plot, and that's a plot for the surface temperature. Now, finally, there are 2 more phenomenon that we need to take account of in our model, both of them characteristics of moisture. Now, the interesting thing about water is it's a much more powerful greenhouse gas, but it can't put itself into the air. The air has to be warm first. It can't initiate its own feedback process. You can throw more water into the air, but it'll just fall back out of it. The only way you can get air to hold more water is to warm it up first. And that's what carbon dioxide is doing, and that's why it's called carbon forcing. So carbon dioxide will kick it out to start with. Say it increases the air temperature by 1 degree. That extra 1 degree will hold more moisture. The moisture content in our universe, in our atmosphere, is currently about 0.3%. In the tropics, before a thunderstorm, it can be as high as 4%. But carbon dioxide will increase the temperature, so it will then increase the moisture content, which will then hold more water. That more water in turn will increase the temperature again. So that might, water, 1 degree of carbon dioxide, the water that's held in there wants to increase it another 3 or 4 degrees. And that could be a runaway effect if it wasn't for cloud cover. The more moisture in the air, the bigger the cloud cover, the greater the albedo. So you're actually cancelling out some of the input energy coming from the sun. Now that albedo can never be higher than about 70% with clouds. Clouds are not a perfect reflector. They cannot reflect more than about 70%. So that means that there's a cap on the negative feedback, which is caused by clouds. So that means that there'll come a time where the temperature is so warm that it has so much moisture in it that the albedo reflects away 70% of the energy, but there's always more energy still coming in. It's not like a mirror. So while there's more energy still coming in that state, you can actually carry on to well over boiling point of water. And this is the process that happened on Venus, where Venus once had oceans, but now its surface temperature is 400 degrees Celsius. That was a greenhouse runaway effect where all the oceans boiled off. And it's interesting to note that we've got 800 gigatons of carbon dioxide in our atmosphere, but we've got 36,000 gigatons of carbon dioxide in the oceans. So once you get the oceans to a temperature where you do run away, then the runaway is catastrophic. So there are our feedbacks. Higher the temperature, we're going to have more moisture in the atmosphere, which wants to make the temperature even higher, but for a while we'll have more clouds, which will try and make the temperature lower. But there will come a time where we will have thermal runaway. And why is water doing this? Water is a strange molecule. And it's got, even though you're H2O, where you've got covalent bonding between the hydrogens and the oxygens, but you will get, with the exposed oxygen, you will get hydrogen bonding, which makes water sticky, keeps it together. But what happens, and what's been observed now, that's interesting, about 200 years ago, Grothus hypothesized that in water, hydrogen ions pass between the oxygen atoms. In 2006, scientists reviewed this and found it to be true. The term proton jumping. The hydrogens are continually networking through the oxygens. This is a weakness for water. This makes it so good at evaporating. You don't have to get anywhere near its boiling point, because when you can actually snip these bonds very easily, they're weak. And especially when a hydrogen is making a transition, so you've got one oxygen with 3 hydrogens and another oxygen with only 1, these bonds can easily break. So when you're evaporating, it's not like it's just single atoms going up into the atmosphere. It's whole droplets of atoms going up. So, and then once they're in the atmosphere, they can start to break down. So it's just showing you why water is so important. And the interesting thing for this sort of feedback is we've got lots and lots of information now. We've got atmospheric moisture for the averages that are coming through from NASA, and we've also got the albedo mean cloud cover data that's coming through. So we can look at the relationships from moisture content to albedo and from ground temperature to average moisture and start to use those in our models. Now I'm just going to go back down to the IPCC scientists' approach of our dear planet. Our modeling has become a little complex as there are many many bits, but each one is chewable. The complete science is a science that climate scientists have to comprehend. Isn't simply complex, but it's complicated. Let's take a synoptic view of it all. Oh, notice in my planet there, notice the moon. The moon is a great mixer and turner of sea and ocean currents and so on. Huge power there. But presenting one of IPCC's own charts, climate science modeling complexity is versus comprehensiveness, we can see that this has got about 3 sets of models: the cause set, the simple biome, carbon cycle, soil, vegetation, and atmospheric transfer models; the process set, radiative convection models, and energy balance models. And here you see it's similar to what I've done. They are a little bit more complicated. You know how we turned away convection and you know, how I decided not to bother with conduction and convection? Well, those little orange arrows are the energy losses that they use, which I'm not taking any account of. These arrows, incidentally, are all all relatively sized. And you see that we're only doing water and carbon dioxide. There's methane there and ozone and, you know, and nitric oxide and so on. There's little bits which the scientists worry about, but I'm not worrying about it. No. So there are the convections for the weather, very complicated. Then there's the atmospheric oceans and general circulation models. And there's sea ice and polar ice models. And then there's integrating the whole of them together. Now, the work that the climate scientists are doing and also the data that's being caught, I would say that we're going to have very accurate modeling, also with AI to do a lot of the number crunching. We're going to have very accurate weather modeling, quite phenomenal weather modeling, where they're actually taking the climate and cutting it down into 100 cubic meter parts to look at wind and so on. It's really quite amazing how we're going. But it means that the models will actually get more and more accurate and dependable. And that is my model. I haven't had time to update that from that. I first developed this back in 2016 and 2017. I need to update it and I need to work on my computer program. I'm looking at about 3 or 4 months of work to get it up and running again. But being an average, like taking an average, it's also very good for taking local conditions and modeling them. Now, we're not finished here. There's 2 other areas that we need to bring in. See, so this model will actually say for an increase in parts per million of carbon dioxide, what will be the equilibrium change in surface temperature? So that gives us our temperature. But once we know what that temperature is in the energy, we have to look at what happens to it, to that energy. And what happens is a lot of the heat that's come out of climate change has been taken up in the oceans. And when we look at the, for example, if we had a 5-degree temperature increase over 100 years, the oceans would take to absorb that 5 degrees would take about 90 years. So we wouldn't feel the full effects of it until 90 years downstream. It takes time, joules per second, with climate change. So carbon dioxide working in the atmosphere will reach an equilibrium fairly quickly, say within a few months. And you can get the surface temperatures from oceans because of the water property. It doesn't need to be boiling at the surface. It's very easy to evaporate. So even though over land you can get surface temperature increases straight away, you can also over oceans. But overall, that energy is being absorbed and taken up by the oceans, and that takes time. So I want to model that to actually get a handle on how long it will take for it to settle down. Now, the other thing that's happening in oceans is ice melt. Ice melt takes a tremendous amount of energy. And when we're looking at the ice loss, that's actually taking heat back out of the ocean. So there's a bit of a feedback there. But all in all, when I was first thinking about 17 meters sea level rise by 2100, I now tend to agree with the IPCC models that are saying it'll be about 5 meters. But my first model came out and did this prediction, and I think now with more information, I'll be able to zero in on it with more confidence. But this first model back in 2017 wasn't too bad. It said that when we started off at pre-industrial levels of 13.5 degrees, I've got some feedback happening now. With a carbon with 270 parts per million, if we doubled that, we would expect to find equilibrium at about 16 degrees from 13.5. Dealing on pre-industrial, that's 1750 before the steam age era, we're already 1.5. We're at 15 degrees now, which is 1.5 degrees. There's your 1.5 degrees. The reason why people are arguing is some people are measuring it from the average of the 1800s rather than going back to 1700. So it's just pedantic as to what reference you do. But what shocked me here was I was finding out that if you increase the carbon dioxide by 2.7 times, we're already doubled it. If you go up to 2.7, from that point onwards, that model would not converge and started to get thermal runaway. You started to get maximum cloud cover, maximum albedo, and therefore the extra energy will just carry on coming in until the oceans are boiling. And that was a lot closer than anyone thought. So I'm hoping to update the model so that I can get more a better handle on exactly when thermal runaway will start, and then to take the model on to see how much actual time we've got. So that's for another presentation. So all up, are we capable of saving ourselves from ourselves? We're in a very, the science is there. It's not that complicated. Even an engineer sitting in Whangaparō can actually go through it with access to the internet and to all the scientific data and come up with our own models that are not bad. I come back to the message on climate change to world leaders, and this is an old one, but it was relevant then and it's still relevant now. Human-induced climate change is an issue beyond politics. It transcends parties, nations, and even generations. For the first time in human history, the very health of the planet, and therefore the basis for future economic development, the end of poverty and human well-being, are in balance. If we were facing an imminent threat from beyond Earth, there is no doubt that humanity would immediately unite in a common cause. The fact that the threat comes from within, indeed from ourselves, and that it develops over an extended period of time, does not alter the urgency of cooperation and decisive action. Are we capable of saving ourselves from ourselves, or are we going to carry on doing nothing? Because at the moment, this is 4,000 scientists in 2014. We're at 2024 now, and we've still done nothing. So I don't know what it's going to take. Now, the other interesting thing is when you get temperatures that are above 37.8 degrees, because that's our blood temperature, when you get 40 degrees is a death fever for a human being. So if you don't have access to water, to swim, or just to keep cool, the air conditioners, a few days at 40 degrees and you die. I think with temperature increase, we're going to exceed these in the tropics quite soon, and I want to model that and see when. When I was over in Singapore, it's interesting to see that their plans for surviving climate change and sea level rise and so on is to go underground where they can regulate the temperature and so on. But it seems to me that we don't need a virus to wipe out most of humanity. The heat in the tropics will do that. Just the heat, just the extra heat in the tropics will wipe out most of humanity, unless they migrate north and south. And that puts New Zealand in rather an interesting position. But that's the question. Are we capable of saving ourselves from ourselves? Now that ends my climate change. Look at the planet turning into Venus. Yeah, let's hope not. No, thank you. Any questions? I'll stop sharing the screen.
Can you stop sharing? Then we can see who is raising his hand, like Adam.
There you go. Right, Adam.
Hi, thanks. That was very interesting. I'm not an engineer or a scientist, but the IPCC reports model the scenarios on radiative forcing. Is the radiative forcing your balanced model of the that you showed at the beginning with the 350 coming in and then 155 going in that circle? Is that the balance that they're talking about in the radiative forcing in the IPCC models?
No, the radiative forcing is is caused by carbon. So say our temperature is an average of 15 degrees. That will hold so much moisture. Right? You can't get more water going into it because it won't stay there. You can throw water into the column, it won't stay there, it'll fall straight back out. So that'll just sit there, and water is the big greenhouse gas. So radiative forcing is when you get carbon dioxide in, and carbon dioxide might take that 15 degrees and increase it to 15.5 degrees. So it's forced the temperature up. Now that it's 0.5 degrees more, it wants to absorb more water. And then the more water that comes in wants to heat it up even worse, 1 degree or 2 degrees. And then that absorbs more water. So once the carbon dioxide forces it, the water will then go in a cycle until it reaches equilibrium. And it will only reach equilibrium if we stay below the maximum cloud cover and albedo. Once we exceed that, it'll just carry on running away, thermal runaway. And that's the danger that we're looking at.
Interesting, thank you. So that's the it's not that energy balance you showed earlier, it's the carbon and the impact on the carbon increases.
That's the importance of carbon dioxide. Without carbon dioxide, we wouldn't have increased temperature. We wouldn't have a global warming phenomenon. So both carbon and water work hand in hand. Water is the big one, but water needs carbon to set it off. So in the past, you know, carbon dioxide layers values changed, you know, with different volcanic activity and so on. We've really changed it, but in the past, it's sometimes carbon dioxide lags temperature increase, sometimes temperature increase lags carbon dioxide increase, but there is that relationship there. where carbon kickstarts the process, and then water takes over and you know, runs with it.
Thank you.
But that radiative model is exactly, the energy balance is exactly it. Eventually we'll hit another equilibrium when it's warmer, and what comes in has to go out, and there'll be you know, you add another blanket on, there'll be, you know, that interestingly enough, when you have a look at how I'm modeling through the universe, and I'm doing it in 3 different phases, it's like 3 blankets. But each of those are going to get more and more carbon dioxide, so they'll absorb, you know, absorb more and then hold more water.
If just want to say thank you very much for all the hours and hours of thought and effort you put into digesting all the information and then being able to explain it. A lot of people just trust the book, but you've kind of gone right into it all. I recall hearing, might have been someone from NIWA about 10, 15 years ago, saying that they felt that the modelling was quite good, but with the data that people were collecting related to climate change, that the models will get a lot better over that 10-year period, which it probably brings us to now, or maybe even past, we're one of it beyond that.
Yeah.
Have from your reading, what's your update on how much the models are starting to be good enough to kind of predict, or are we still kind of calibrating them based on all the data that we're collecting? Yeah, how well have the models been tested by the incoming data so far?
It's absolutely getting better and better as each month passes and more data is collected. But what happens with scientists is they want to get a handle on what the process is. And to get a handle, they might go down several rabbit holes and write lots of papers on it. So when it comes to the relationship between, nothing is simple in the universe, but when it comes to the relationship between moisture content and cloud cover, it's really complex. So you can spend a lot of time trying to model that in the international community of scientists. But there's a quicker way we can do now, is from an engineering approach, and that's just to get our NASA data on, you know, the albedo for the year across the whole planet and the moisture content for the year across the whole planet. All this data is now coming in, and it's free. You know, that's one of the wonderful things that scientists do so far. So we can get that, and we can start to look at relationships now with 20 years of data collected of moisture content to cloud cover. And sure, scientists will in the end come through with laws and formulas and ways to calculate and predict, but we can actually do our approximations. And the other thing that I'm interested in modeling like this is I'm only really interested in temperatures changes up to about 40 degrees or 50 degrees. I don't really need to worry about modeling the planet when it's going to go into thermal runaway, because 50 or 40 degrees for an average temperature means most humans will be dead. So working from 15 degrees to 50 degrees is mostly linear. So if I see a trend, we're not going to be very wrong. And I don't mind being plus or minus 20%. As an engineer and what I design to. Stress grade timber for all housing is plus or minus 20%, and we do a wonderful job with that. I don't mind, whereas scientists will mind, and they will fret about it, and they will, you know, carry on and get research and write papers. But there's a difference between scientists and engineers, and I think what I was hoping to do with this was to look at the whole situation, which on face value seems terribly complex, and realize that it's not. All engineers, we've all seen there's nothing that tricky in what we've just modeled. We can understand it, and when we know it, we can be convinced enough to actually go out into the public arena and just insist that our politicians actually start to do the right thing. That we haven't got more time. We don't need to wait for more science.
I have a question, Jeff, if I may.
Yes,
Thank
Lindsay?
you. Thank you. Fascinating presentation. And I probably struggle more than most to keep up, but I think I still got a lot of it. I've got two questions. They're both interpretation questions. One of them, towards the end, you had that chart of global warming and you referred to the significant difference between a factor of 2 and 2.7, but I wasn't clear what units you were talking about. Are they some sort of multiple of pre-industrial carbon dioxide levels?
Just a straight out. So pre-industrial level, 1750, the carbon dioxide was 270 parts per million. And now we're 410, but there's been a lot of extra uptake in the ocean. We've actually started to deliver, we're producing 540, we're up to 540 parts per million, but the Earth is still absorbing some of that. So when it comes to production-wise, we've already exceeded double.
Okay. Yes, so maybe that's a third question, but my other interpretation question was back when you were talking about the energy balance and especially the re-radiation from Earth. You talked about the heat going up and then getting trapped in the greenhouse gas layer and then going equally up and down. And I was a bit struck by the fact that they were exactly equal values going to space and back to Earth. And there may be some fundamental there that I'm not aware of. But can you just explain why there's that parity between those two values?
Yeah, so when it comes to convection contained in the troposphere, now radiative heat carries on right through the universe.
Okay, thank you.
But in our weather, in the warm air rising to form clouds and then falling down and rising again and falling down, it's that energy is staying in the troposphere and it causes our weather. So there are some losses. So a warm air packet has got energy. It rises up, or cold air falls through it. It rises up to the top of the troposphere. It condensates and forms clouds. It then cools down and carries on. So the energy is circulating. When I went to the IPCC model, they had those little orange arrows.
Yeah.
That's their estimate of what losses there are in both conduction through collisions with atoms and so on, and in the troposphere and the convection areas. So because they're so tiny, I just not even, they're sort of well within my plus or minus 20% range. So I don't need to get that complicated to deal with it. But yes, a lot of papers, a lot of people have actually modeled it.
Thank you. I'll let others ask questions before I ask my next one.
Jeff, just a clarification to Lindsay's first question. We have not doubled the amount of CO2 in the atmosphere. We are measuring at the moment 425 ppm. So this is not twice 250 or 270. But we are putting lots of CO2 into the atmosphere in terms of tons of CO2. And that has multiplied 1,000 millions times since pre-industrial levels, of course. But I think you have to be careful to be understood by other people. You can't claim that we are putting from the ppm levels, we have doubled the amount of CO2 in the atmosphere.
Yeah, well, what happens is because this is the second part of my presentation stream. So the first part is the causes. And in there, I go to a lot of trouble of actually looking at the data for how much carbon we're producing and how much is actually staying in the atmosphere. So we're still at a stage where there's a gap between what we put into the atmosphere and what stays in it. So that's the capacity of the oceans to take it up and all that. So when you have a look at the gap, if it wasn't for the oceans taking in more carbon dioxide, we would have hit 540 parts per million. We put that much there, but the planet is, because it's a very stable planet, It tries to fix itself. But in the end, we are actually, it's the curves diverge, but they're starting to join up again. We're actually starting to go, we've gone past one of the tipping points of the actual planet able to absorb and to contend and to try and correct for what we're doing to it.
Yeah, I agree with that, yes.
Yeah. So yes, it's 410, 425 parts per million, but we're actually dumping into it enough for it to be 540. So we've got a long way to go to cut carbon dioxide before we get into anything safe.
Jeff, can I ask a question? You didn't say very much about methane. What's your thinking about the part that methane might play in all of this analysis?
It's getting more important. I just haven't done it because it's still measured in parts per billion. It's still, I mean, it's probably the worst of all greenhouse gases, and worse than that, it finishes up as carbon dioxide when it does break down in the atmosphere. So it has a horrible time. It's about 20 times more potent than water as it starts off, but then it finishes up as carbon dioxide at the end of the day, which will then stay up there for thousands of years. So it's going to play a big role because we're actually starting to melt permafrost and so on, and we're going to get a lot of methane coming out of that. So that could really upset things. Another really interesting thing to happen when I've been studying ice too, and trying to model the slump and the flow rate from the glaciers over Antarctica, is we're now getting an answer to why, you know, when the whole world was stopping CFC emissions, and we all agreed that to curb CFC and stop it altogether, we're still getting about a third of what we did back in the 80s. Where was it coming from? And people were looking at China and so on. It was too hard. What's actually happening is it's likely to be coming, it's now sort of measured in Antarctica, it's coming out of the ice. It was CFCs that were trapped in the air bubbles in the ice, and as that ice is melting, it's going straight up into the into the ozone hole above Antarctica. So we've got these things too. And the other thing that's coming out of the ice is lead, the lead we put into petrol. So we've got a few problems.
So what you're saying, Jeff, is that currently the carbon dioxide is far and away the more important thing to consider. Methane is an upcoming problem, but it's not comparable to CO2 at the moment. Is that right? Yes. Yeah, thank you.
So it's a big deal for New Zealand because half of our emissions are methane. Yeah. So we're about 46 odd tons per person per year, but our consumption is only 21 tons. The rest of it's our dairy industry. So it's important to us to get our overall emissions down, just to lead the way. But it's not important in the world, but it can become very important if the permafrost starts to melt and really, and it looks like that's what's going to happen. In which case, there will be a time where our models will have to take that into account.
Right, thank you.
Be practical.
Thank you, Jeff. You've looked at a lot of the science and made it into a clear format for us to be able to understand and incorporate it in your models. I was wondering, have you looked at, I suppose different scenarios, but for one is like our current amount of carbon dioxide in the atmosphere, what that means like 100 years time and 200 years time for sea level rise?
Yeah. Now, what I need to do is spend about another 3 months on my models, which I want to do because I think it's really important. And that's where I'll take. So what I would like to do next time is when I've got the computer working with the model that I've just presented to you, then I want to have like a seminar with you guys where we agree on the inputs and the weightings and so on to go into it. And then out of that will come the temperature. So we'll say, okay, what are we going to do? What's going to be the average carbon dioxide, we're putting into the atmosphere between now and 2100? we'll put that figure in and we'll see what the temperature will be by 2100. And then what I need to do is model the ocean and all that to see what time it's going to take to finally put a timeline on it. Okay, if we put this carbon dioxide in, there will be a slow increase in temperatures. It might take 90 years before we've heated up the oceans enough for equilibrium again. And so we'll know that at the end of 90 years, we'll be 5 degrees hotter right across the planet. But in the meantime, we're going to go from here to there, and it's going to take 90 years or 70 years or 60 years or whatever it comes out. And that means I've got to model the heating up the water column in the ocean, but I've also got to subtract from that ice melt, because that takes a whole lot of energy back out of the ocean, and it takes a lot of energy to melt ice. So, you know, and with the glacier slumps, and, you know, I'm trying to model Antarctica by using a cap and saying you're 3 kilometers high at the center, the radius of Antarctica. If we take away the sea ice from around it so that it can slump into the ocean, what's the flow going to be from that, you know, to get a handle on how much ice we're going to, you know, is going to go into the ocean, which will then need to be melted and take energy out of it. So we'll get a timeline. So
this time lag effect is very important for us to know about, and well, to have some understanding of that the effects we're seeing now today from climate change and sea level rise is just the very start of a slow process of the sea rising. So when I'm very interested in the last ice ages, like 10 to 20,000 years ago. My understanding is with a 6 degrees difference, we had a 125-meter difference in sea level, which is just a vastly different planet, vastly different coastlines. Well, for a start, we didn't need the Entente Ferry because the two islands were linked together, because the sea did not separate the two, North Island and South Island, but just the geography is so different. Toronto, Canada had a couple kilometers of ice on it, and much of North America was covered in ice. And it just seems if there's a long period of time, the quite small changes in temperature have a massive effect over the long period, but there's that lag in it which reduces the effect now and within the timeframes the IPCC talks of, but over longer term it's even worse.
Well, I think that I think one of the things that have happened, I mean, I was at the Complex Processes Research meeting with philosophers the other day, and they were asking what's happened to our leaders, our technical leaders and so on. And we've been a little bit stymied. We are so overwhelmed by the amount of knowledge available to us now that we haven't acted. And I think it's very important for me to actually finish this model so that I actually can get a really good handle on what timelines we're looking at, so that we can then start to insist through the media and all that people actually do the right thing and get on with it. And so that's really that's the motive behind the modeling. But yeah. Just to see, we know that there'll be the first meter by 2050 of sea level rise, but what will there be by 2100? It's you know, my first modeling is showing something like 17 meters. So, but I want to refine that and get that right and get that out to engineers so that we can all look at it and try and pick holes in it and so on, but let it settle down so that we can actually take our role in our society. And I think engineers are natural leaders rather than scientists. Scientists are a different type of person, whereas engineers, we are used to dealing with the people. We interface between science and the people. And I think that the leadership should start to come out, engineers should start to stand up and say, no, you know, never mind the political arguments and so on, this is what we need to be doing, and let's just get on with it and do it.
See, if I can pick up the question I was going to ask before. First of all, a comment. I think you're exactly right when you talked about your pragmatism and plus or minus 20% and what you've just been talking about. I think I've been in a number of climate conferences in New Zealand and overseas, and several people have come up to me afterwards and said, oh, it's good to have a practitioner here. And I think, so I'm more power to your elbow on that. What I really wanted to ask was, and you've touched on it, and maybe it's in your next session, is the trajectory of the oceans as a buffer against atmospheric disaster. And the feeling I have is that that buffer is approaching capacity, but I have no real sense of how close it is. You talked about 90 years and so on. Will you be covering that subsequently, or is that something you'd be willing to comment on now?
That's exactly what we will be, you know, that'll be another presentation. So first one is to get this model up and working and to get the buy-in from my fellow engineers and so on about how to set it. We've got 3 points, data points to calibrate our machine. Firstly, we can start off with no greenhouse gases. That's the minus 19 degree one. And from there, we can work out up to the pre-industrial age of 1750, where we know the carbon dioxide layer level. We've got a good idea on what the average temperature was, but we don't know the moisture content. So we can calibrate it because it'll tell us what the moisture content is. That's the good point. And then we've got another point of today, going from there till today, to make sure that we're still online. So we've got these 2 points that we can use to calibrate. Once we can calibrate that, then we can say, yeah, well, this is what the temperature is going to be. And if it's going to be 5 degrees warming, you know, so we're going to be 5 degrees hotter. When? Is that going to be 100 years or 200 years? That's when we've got to go into the oceans. That will be the next layer of modeling to find that out. But once we know that, I think we're in a place as engineers where we can stop worrying about the science and get on with the practical social obligation of getting something done. Stuart.
Jeff, thank you very much indeed. That was absolutely brilliant. I spent my working life working with some of the large companies in England, reducing their energy consumption, and on very big projects. And it's been very plain to me for a long time that you just cannot rely simply on politicians to do the right thing. I'm non-political. I'm not interested in which party it is. They just don't have they're not scientists. I'm an engineer and I'm very proud of that. But I don't see that they have the knowledge, the understanding, the science, the regulation, the skill set to actually understand what the problem really is. And yeah, put me down. I will be there to try to help if I can, to put the point across. But it's not to politicians. It's going to have to be the community, because I think we're moving more into a time when community is more important, and I think politicians are probably less so.
Well, an interesting thing happened with COVID. The world shut down. Society's just shut it down. They didn't go to all the multinationals and say, hey, what should we be doing? It was a crisis. We all know that with sickness like that, isolation is the best thing to do if you don't understand it. And the world shut down. So it can be done when it's serious enough. You know, we can start to, I believe we can start to get, we can start to be positive. We can start to take some positive work on. We can start to make the right steps. So we know what the responsible thing to do is, and now we have to, as a society, choose to be responsible or reasonable. That's the next step.
100%.
And so we'll do this modeling so that we, so that we can go out in confidence and say, look, we're not mucking around. The jury's out now, and now we're going to act. And we've got a timeline to act, and we can,
The work that I understand that IPCC do is quite compromised because of the individuals that are there at the IPCC conferences.
Yes.
Far too many petrochemical people, paid lawyers, different things, and it's there, or it's all there to confuse, delay, whatever, and we've confused and we've delayed for long enough, and we need to take some positive action. And I'm right behind you.
Well, I think, the communication, when I was doing presentations like these, if you have a look through the presentation in your own time, you can see that there's not a single thing that can't be understood that's too hard. It just breaks it all down into a simple process, every bite-sized processes. It's a bit like a storybook. I'm using PowerPoint as a storybook there because I'm still really keen on the setting up a platform and working out what our hot takes are going to be, and breakdowns and so on, what templates we'll start to use for that. But I think that will all be part of what we do as engineers in the future, starting to, once we know what to say, then going out and saying it, and just being bloody minded about it with people. With misinformation and
May I pick up on something that Stuart just said? Stuart, I'm sorry I talked across you before, by the way. I think your comment about citizens, it moving away from politicians towards citizens, is incredibly important. And I think within the process you're talking about, Jeff, and I just want to say that I think it's, staggeringly important that we help you pursue that. The idea of how the information is disseminated is also something that needs to be nurtured in parallel with that. And I think, with all respect to the present group, we probably don't have the nous and the PR capabilities and so on to do that. I'm not suggesting we rush in there now. I'm just meaning that we get to the point of, you were saying, we know what our message is going to be. We should be on the starting blocks, knowing how we're going to disseminate it. I will just leave it at that. Thank you. That was incredibly valuable.
Thanks.
Otherwise, I'd like to thank you, Jeff, for a very good presentation, very in-depth, far too high for my average knowledge of engineering. I might have to look up a few things to really be able to follow you. But nevertheless, it looks, from a plausibility test, it looks all right so far. And I'm looking forward to the next presentation, where you come up with some numbers and some scenarios that are then close to reality, and we can see what's coming towards us. So thank you very much for all the time you have spent.
It's a pleasure.